All right, we're talking about 3.2. There's two theorems in here that I'm going to teach you about. One of them, believe it or not, is not really an AP theorem, but it's a good theorem. And the second one is one of the most important theorems that we'll be talking about all year long. Okay, so 3.2. The first theorem is a French guy, and how would you pronounce it? Any French scholars in here? Roll. I usually just say roll, you know, like, can you pass the rolls, you know, that kind of thing. I don't know. Do you know how to pronounce it? Roll. Okay, I like that. So we got Rollo's theorem, and then we have the MVT. We've already had two other VT theorems this year, right? We had the first one was the IVT, and then the EVT, and now we got the MVT. MVT, you got to be careful how you say that. That is MVT. It is not VH1. Okay? You got to be careful how you say that. MVP. Oh, MVP. You know, I was thinking like MTV. That was a little subtle MTV thing. Yeah, anyway. Yeah, but MVP also. Here's Rolle's theorem from around 1691. 1691. That's a long time ago. His name was Michel. First name, Michel. Or Michael Rollet. I have no idea. Are you getting the pronunciation from Google? Okay, one more time. Okay. So here's Rolle's theorem. Rolle's theorem. I've never known how to pronounce it. I don't know if I was ready for that much phlegm in the back of my throat. Let f be a function that satisfies the following three hypotheses. Three of them, okay? These are three ifs that need to be met in order for Rolle's theorem to apply. Number one, f has to be continuous on a closed interval. Been there, done that, seen that before, right? That is the single hypothesis for the other two VTs that we've already mentioned. Rolle also said that f has to be differentiable on the open interval, which means, like Kenny G saxophone playing, it has to be connected how? Smoothly, right? Now notice we're freeing up the endpoints. We're not claiming it has to be differentiable at the endpoints because, can it? No, the derivative won't even exist at the endpoints because it has to exist on both sides. But that means that everywhere between A and B, we can't see any what? If it's continuous, where would it be not differentiable if it's already continuous? Cusps or vertical tangents. Okay, good. So it has to be smoothly connected, but we can't have any cusps or vertical tangents. And here's the last thing of theorem. Don't choke when you say that. F of A has to equal F of B. We're on the X interval from A to B. If F of A equals F of B, we're saying that the Y values at the endpoints must be equivalent. Same, right? If you're walking through the woods and you stumble across all three of those things, if they all happen to be there in one place, how often does that occur? I don't know. We'll see. But if you have a function that's continuous on the closed and it's differential on the open and the Y values of the endpoints are the same, then here's what Rolle said is guaranteed to happen. There's going to be an X value on the open interval. That's muy importante, as he might not have said, such that the derivative there is 0. There has to be at least one X value strictly between the endpoints. Can't be an endpoint where the derivative is equal to 0. Graphically, that means there has to be at least one place where the tangent line is what? Horizontal. Now, this is an existence theorem. Didn't tell us. He didn't tell us how to find it. He just said that it would exist if those three things happened. Here are some functions that satisfy all three, okay? Notice I have from A to B marked. This function, of course, is continuous on the closed interval. We got the two endpoints there connected to the graph. It's differentiable on the open interval. There's no cusps or vertical tangents in betwixt there. And the Y value at A and B are on the same graphical elevation. They're the same. The theorem then, I'll just say the theorem, because my throat is getting sore, tells us there has to be at least one x value strictly between the endpoints where the derivative is 0. This graph has more than one. Here's a line that points to a value of x where the slope is 0. Here's another one, c sub 2, that points to a place on the graph where the slope is 0. Are those the only two? No. This graph actually has how many values? Infinitely many, because it's a horizontal line. All the x values have slopes to 0. But thank you, Roll. Thank you, Roll. I'm just going to say Roll. He gave us the assurance that we knew we were going to have at least one. Well, this one has infinitely many, which infinitely many is more than one, right? So you could have more than one. His theorem guarantees at least one. You ready to see another one, less trivial one? Okay, here's where Roll was really getting into things. Here's the function. The y values at the endpoints are the same. It's continuous at the closed interval. It's differential in the open. There has to be at least one place where we have a horizontal tangent line. At least one horizontal tangent line. This one only has the one, right? It only has the one. There's an x value strictly between the endpoints where the derivative is 0. Whew. Okay. Good thing we have one because it was a guarantee. It was a guarantee. What about this one? Oh, that's this one. This one has how many? 2. Does it have more than 2? No. 2 is more than 1. We're guaranteed at least 1. We could get bonus ones. Here's another one. Okay. Do you need to see more examples? What do all three of these functions have in common? The if parts. What are the three if parts? Continuous on a closed interval, differentiable in the open, same y values at the endpoints. Okay, good. As you can see, I'm not going to try to say that. He gave us the necessary conditions in which we're guaranteed to have a very special critical value. Why is it a special critical value? It's where the derivative equals 0, so it's special because it's a horizontal tangent line. Those are the smooth ones, okay? So if you think of the position of an object that is thrown straight up from the earth and then caught again at the same point, okay, we throw an object up and we let go of it right here about 5 feet in the air. We're awesome, so it goes straight up. There's no wind. It comes straight back down and lands on our hand. The starting position and the ending position were exactly the same. As it traveled up and came back down, its position was continuous on the closed interval from time 0 to time end, right? And it was also differentiable because if we're talking about the derivative of position, we're talking about its velocity. And if we have infinite slope, that's infinite velocity. Could the ball actually go infinity miles per hour as I threw it up? No. So it had to be differentiable. Then Roll guaranteed that there had to be some place between the time I left my hand and the time I caught it again, awesomely in the exact same spot. There had to be a place where the derivative of the position was 0. That's where the velocity would be 0. Thanks, Roll. I know it exists. What would that be? That would be the point at the very top, right there before the ball came back down. Okay, thanks, Roll. Nice. It's nice to know that that's going to be there. Now, just because Roll's theorem doesn't apply, does that mean that we're not going to have a horizontal tangent? No, because if you look at this right here, if this were open, would Roll's theorem apply? No. It would be continuous on the open interval. It would still be differential on the open interval, but now the y values, the endpoints aren't the same either, and of course, we still have a horizontal tangent. If that were still closed, but now this was an open hole right there, Roll's theorem would not apply, but would we still have a horizontal tangent? Yes. Now, it could be that Roll's theorem doesn't apply and you don't have it. Here would be an example, right? You have a y value being the same, a y value being the same. Go up, cusp, come back down. Oops, that was a loop. There we go. Does Roll's theorem apply from A to B? No. I was trying to make these the same elevation. So let's say that it's continuous on the closed interval, right? And f of A equals f of B, but it fails because it's not what on the open interval? Differentiable. Do we, in fact, though, still have a horizontal tangent line between A and B? No, in this case we don't. Whew. Good thing Roll's didn't apply because Roll's theorem guarantees at least one and we don't have one. Good thing Rolle's doesn't apply. That would contradict the theorem. In math, you don't call just anything theorems. If you call it a theorem, it's an immutable law, right? It has to be correct all the time, every time. And Rolle's theorem is. But he is kind of very specific, right? If this happens, and then this happens, and then this happens, and this also happens at the same time, and then if this also happens, if all 3,000 of those things happen at the same time, then you're guaranteed this, right? It's like, oh my gosh, that's a lot. That's a lot pending, right? How often does that happen? Well, let's look. Example 1. For f of x equals that on the closed interval from -2 to 2. Determine if Rolle's theorem applies. And if it does, find the value or the values, foreshadowing, of x equals c, guaranteed by the theorem. Okay, Rolle's theorem, does it apply? Well, we got to think of the 3 ifs, right? Rolle's theorem only applies if it's continuous on a closed interval. I have a function that is crossed out now. How about this? I have a function that is what anomial? Polynomial. Gosh, polynomials are nice because they're not only continuous everywhere, but they're also what everywhere? Differentiable. Okay, so it's going to be continuous on the closed. It's going to be differentiable on the open. All I got to do is check what? Yes. Let's figure out what f of -2 is, and let's figure out what f of 2 is. Check. I didn't even compute what they were. What's up with that? Can I just say that? I can. Why, Brandon? They are equal. But without actually computing the y values, how do I still know they're equal? This is an even function. Good. Yeah. And remember that negative inputs and positive inputs have the same output because I have only 2 x's and they're both raised to even powers. So you could say since, you could put the reasoning first, since f of -2 equals f of 2, comma, and f of x is, and you want to again speak straight to the theorem, is continuous on the closed interval from -2 to 2 and differentiable. Diffable will abbreviate on the open interval from -2 to 2, comma, this guy's theorem applies. Okay, so Rolle's theorem basically says what goes up must come down. Yes, that's essentially what Rolle's theorem says. What goes up must come down. Or what never goes up must never go down, I guess. I don't know. That's the horizontal line. So this graph is going to turn around somewhere. It's going to have a vertical turning around point. It's either going to be a local min or a local max with a nice horizontal tangent. All right, so how are we going to find it? Rolle's theorem is an existence theorem. It just tells us the 3 conditions needed for it to exist, but now we have to find it. It said to find the value. How do we find it? How do we find critical values where the derivative is 0? We set the derivative equals 0. Do we solve or solve? Solve. Yeah. So let's go ahead and take the derivative. F prime of x is 4x cubed minus 4x to the first. And we set it equal to what? 0. Why 0? That's what the theorem is guaranteeing. It's guaranteeing a place where the derivative is 0. And of course, then we factor out a 4x, and we get x squared minus 1, still equal to 0. And from there, we can go straight to the solutions, right? X equals 0, -1, +1. Yay! That function has 3 critical values. We box them up, we walk away, yeah? No. We always have to make sure we're answering the question. It said to find the values guaranteed by Rolle's theorem. Rolle's theorem is guaranteeing a C value strictly where? In between the endpoints. So here's the thing. We need to look at all of our critical values and make sure that they are on the open interval. Of course, if they fall outside the interval, do we count them? No. What if they fall at the endpoints? No. Very good. The Rolle's theorem and the MVT as well, as you'll soon see, guarantee values strictly between the endpoints. And you might get a question where a critical value shows up and it is an endpoint, and that's the College Board and me being sneaky to see how well you know your theorem. If it is an endpoint or outside the endpoint, you cannot include it. So, returning over here, which of the three, if any, are in the open interval from -2 to 2? 0, -1, and 1. All three of them are. Yay. Okay. So Rolle's theorem guaranteed 1. We actually got 3. And that's it. You're done. What if one of them wouldn't work? Then we would do that. Okay? All right? So make sure that they are in the open interval. Check to make sure to see. Check to make sure to see if. Check to make sure to see if they are in the open. Sorry, you can refine that better. In the open interval. Check to make sure to see. To verify. Check to make sure to see. To verify that they are that they are actually included within they that the critical values found are actually included within the open interval. Open interval. I can't emphasize that enough, because the IVT and the EVT allowed for those existing x values to be on the closed interval. They allowed the value to be an endpoint. Okay? The IVT and the EVT allow the values that we're looking for to be at the endpoint. But the Rolle's theorem and the MVT require it to be where? Open interval. Okay, so if you get a test question where one of your values is an endpoint, you don't include it, right? Oh, good. And it's easy to cast out the ones that are outside of there. All right, if you want to see what that graph looks like, feel free to graph it on the calculator, but if it's an x to the 4th and it has 3 critical values, I kind of know that it's going to do something like this. It's going to look kind of like a W. And I have a horizontal tangent line there, there, and there. And I know now that all 3 of those horizontal tangent lines fall between -2 and 2, right? So the local behavior takes place, the interesting local behavior takes place between -2 and 2. We can actually then determine, just by the end behaviors and that, if each of those critical values are actually local max or mins, right? At 0, we must have a local what? Max or min at 0. Should have a local max because it's the one in the middle. +1 should be the location of a local what? Min. And 0 or -1 must be the location of a local min. Now, one of these 2 local mins, right, either at -1 or 1, also have to be an absolute min, right? What theorem guarantees one of those is the absolute min? Sorry, it ends with VT. Not the IVT. EVT, the extreme value theorem, guarantees one of those. Yeah. Okay, cool. Interesting. Thank you, Roll. Now, years after Roll, we are on a roll. Many years after Roll came along, came this guy. And he has a forlorn look on his face, but don't be fooled. He really enjoyed what he did. He just didn't have much of a sense of humor. This is Joseph Louis Lagrange. You're already graffitiing him, yeah, bug eyes. We can put him with the milkman, although this guy's not as fun to torment. He's already tormented. He came along and took Rolle's theorem, Joseph Louis Lagrange, and he'll come up a lot. The last thing we learned this year in BC at the end of the year is Joseph Louis Lagrange error-bound. Error-bound, okay? And his name is Lagrange. That's what we usually say. But he was also a French, Lagrange. Brilliant guy. He loosened up the restrictions from Rolle's theorem, because remember, Rolle said if this happens and that happens and then this happens and that happens and this happens and that happens, if all those things happen, then you're guaranteed this. And Lagrange is like, whoa, that's too many things, man. It's too many things. People aren't going to remember all three of those. So he said, I'm going to get rid of one of those restrictions, okay? And, of course, if you get rid of one of the restrictions, you can't make the same claim anymore, can you? But what can you say? Well, you could say something that's actually more general. Now, which of those three restrictions right there do you think he got rid of? Which one seems like it's very unlikely to happen most of the time? Yeah, how often does f of a equals f of b? I don't know. I haven't been collecting data over the years. But that's the one that Lagrange said, really? Really? That doesn't happen that often. But if we have these special functions that are continuous and differential everywhere, like polynomials, then on a closed interval, what if the y values aren't the same? What can we say then? And he came up with this theorem that basically supplants Rolle's theorem. We don't really need Rolle's theorem anymore, just like we don't need the Pythagorean theorem anymore, right? Because we have the super Pythagorean theorem, also known as the law of, no, the other one, cosines, right? But we still use the Pythagorean theorem, even though we have the law of cosines. Why is it the super Pythagorean theorem? Because the law of cosines works for not just right triangles, but for all triangles, yeah. So once we have the mean value theorem, we really don't need Rolle's theorem anymore. But you know what? It's kind of nice to give credit to the mathematical forefathers. But I don't even have his picture here like I did Lagrange, because I don't know if Google Images even has one of so. Okay? You can find one if you want. Here we go. This is called the mean value theorem, or MVT for short. And this is probably one of the most important theorems we'll talk about all year long. MVT. Now, we had the intermediate value theorem. Intermediate kind of implies something in between stuff. We had the extreme value theorem. Extreme implies eating Mountain Dew and Doritos while snowboarding off a cliff, right? Big Y values, small Y values. What does mean imply? Very good. It's not mean like mean. It's mean like average mean. So you can replace the word mean here with average. It's the average value theorem. Okay, the average value theorem. But we call it the mean value theorem. Here's what it says. Let f be a function that satisfies the following two hypotheses. Not three, but how many? Only two. We're in here till 11:20, by the way. If we have a function f that's continuous on the closed interval, that's still important. Okay, that's like the IVT, EVT, and Rolle's. And let f still be differentiable on the open interval. Okay, I got that. We don't have to make the claim now that the y values at the endpoints are exactly the same. Okay? Now, we can't say the same thing. We can't say that we're going to have a horizontal tangent line. We can't say what goes up must go down because we don't know if it's actually coming down. It may still be on the way up, right? We can find it at any given time. Here's what he says then. There is a number x equals c in where? Open interval. That's super important still. There has to be a time between the start and finish. There has to be an x value between the a and b, strictly between a and b, such that not f prime of c equals 0. If you put a 0 at the end of that equation, you have Rolle's theorem. Here's what he says. Such that the derivative at that moment equals not 0, but this. Oh, I see what you're doing there, Lagrange. You're saying that there has to be an x value somewhere between the open interval where the instantaneous rate of change, f prime of c, equals the average rate of change. Oh, I got it. Average rate of change, average value theorem, mean value theorem. I get it. I get it. There has to be at least one moment where the instantaneous rate of change equals the average rate of change over the interval. That's the difference quotient, right? F of b minus f of a. If you do it in the Newtonian perspective, there has to be at least one time where the instantaneous velocity equals the average velocity. That makes perfect sense. If you drove from here to San Antonio and you averaged 55 miles per hour, then Lagrange's theorem says there had to be at least one time on the trip between the start and finish where you were actually going 55 miles per hour, right? And I think we can all say, Yeah, I remember that time. No, we probably wouldn't, but we realized that you can't get up to 80 miles per hour from zero without passing through what speed first? 55. Yeah, okay. This also means that if your grades at any given moment, if your average in the class is a 70, then there has to be at least one time during the 6 weeks where you made a 70 on an assignment. Is that right? You can have a 70 average without making a 70 on an assignment, right? You could have 100 on one assignment and then a 40 on the second assignment. And of course, then your average would be 70. And why are you getting 40s on your assignments, guys? Why would the theorem not apply in that case? Grades are not like continuous, like man, right? Right? They're discrete, finite grades, right? Here. You don't make grades everything in between a 90 and a 95, right? I gave you a 90.263753221111073 on this assignment. Oh, man, I thought it was at least worth a 90.55777222334. Man, I was really hoping for that extra billionth of a point. I put a lot of work into there. It doesn't work like that, right? Grades are not continuous. But positions are, velocities are in the real world. Now, if you think about it from a Leibnizian perspective, he's saying that there's an x value on the graph of f where the slope of the what? Line? Tangent line is equal to the slope of the secant line. There has to be an x value where the slope of the tangent line equals the slope of the secant line, where the instantaneous rate of change equals the average rate of change. I get that. Let's look at some applications. Here's the graphical implication. We have this blue graph from A to B. It's continuous on the closed interval from A to B. We got the y values at the endpoints tethered to the graph itself. It's continuous. There are no cusps or vertical tangents on the interior, so it's differentiable in the open. Do the y values equal each other at A and B? No, but they don't have to for the MVT to apply. If you first then draw the slope of the secant line, which would help you visualize that slope, then the theorem guarantees there's going to be at least one x value strictly between the endpoints where the tangent line has the same slope. And of course, lines that have the same slope are what allow? Parallel. So if you took the secant line slope that you draw first to visualize the slope, you can slide it. And I think we can do that here, right? You can slide it. I trace over that. You can slide it until it touches the graph at one spot, right? Right there. And then that value of x where the tangent line is parallel to the secant line, that's the value guaranteed by the theorem. And we know it's going to be there. This one has how many such x values? 1. Could we have more than 1? Yeah, we could have more than 1. But the theorem guarantees at least 1. Here's a function that's continuous from A to B. If you draw the secant line first, there it is. That's the average rate of change of this function from A to B. Slide it till it's parallel, and it touches the graph at 2 different places, C sub 1 and C sub 2, on the open interval. That's pretty awesome. Now, why do we not need Rolle's theorem anymore? Why does this supplant Rolle's theorem? Sorry, Rolle. What's that? Yeah, the mean value theorem works in Rolle's case. In fact, Rolle's theorem becomes a special case of the mean value theorem, right? Okay, because if this is A and this is B, then by the mean value theorem, there has to be an x value where the slope of the secant line equals the slope of the tangent line. Let's go ahead and draw the slope of the secant line. If f of A equals f of B, then the secant line is going to be what? Horizontal. And if I slide that line until it intersects right there, then the mean value theorem guarantees there's at least one value where the tangent line is going to be the same as the secant line. So there you go. Rolle's theorem becomes a special case of the mean value theorem. If you were to compute the average rate of change, let's see what it would look like in a computation. The mean value theorem says there has to be f prime of C sub 1 such that f of b minus f of a over b minus a equal to each other. Well, what is the numerator going to become when Rolle's theorem applies, when f of b and f of a are the same? You get what? Yeah, if f of a equals f of b, then the numerator becomes 0, and 0 divided by any non-zero number is what? 0. Okay, so it works. Thank you, Rolle's theorem. You kind of paved the way, right? And that's usually how things progress. You have these special cases, and you observe, and you notice patterns, and you make claims. And then you're like, ooh, can we now make a more general statement based upon that? And that's how things evolve. And right now there are people looking for the single equation that defines the whole universe, right? They haven't found it. Chaos theory. What's that? Y equals mx plus b. Yeah. Yeah. They're looking for an equation that combines all of the electromagnetic forces, the weak and the strong, and the force of gravity. They're looking for a single equation. And they're thinking it's there, and it's probably going to be concise and elegant. Maybe it is y equals mx plus b. Maybe it's right in front of our face, and we're just like, get out of there. I'm trying to find this equation. Right? Anyway. Maybe it's 42. Y equals or x equals? X equals, vertical line. I like it. Okay. Let's try example 2 here. Determine if the MVT applies to this function on this interval. If so, find the value of the values guaranteed by the theorem. So this is the type of question that when it invokes the name of the theorem, it's basically testing, do you know the if part, do you know the then part? Okay? So to prove that it exists, well, let's see. We have a function again that is x cubed minus x. It's a what polynomial. So when you're handed polynomials, it's pretty easy because you know they're continuous and differentiable where? Everywhere. So on the closed interval that's given, yeah. So does the MVT apply? Yeah. So here we go. MVT applies. We'll answer the question like this. Since, or because, if you like that, f of x is continuous on the closed interval from 0 to 2 and diffable on the open interval from 0 to 2. Nice. So we know there's going to be at least one x value between 0 and 2 where the instantaneous rate of change equals the average rate of change. Well, it's an existence theorem. It just tells us, okay, if these two things happen, then you know it's going to exist. It's going to be there. But it doesn't necessarily explicitly tell us how to find it. This question asks us to find it. Can we find it? Yeah, you could actually use the conclusion of the theorem to help you find it. Because here's what we know. And I would set it up specifically like this every time. Therefore, we know that f prime of c. Now, you could call it c if you want, or you could just call it x. Okay, I think I'm just going to call it x.
Teachers, please find
we know that f prime of x, for some x value between 0 and 2. I don't think getting caught up with the c is going to be kind of silly. I know there's some place where the derivative at some x value is equal to the average rate of change from 0 to 2. So I'm going to write that as f of 2 minus f of 0 over 2 minus 0. I am going to insist that you show that step every time when it's a mean value theorem. Okay? That's using the function's name. You're setting it up in general. F prime of x for some x between 0 and 2 is going to equal the average rate of change of that function between 0 and 2. Difference quotient. Now all you have to do is fill in both sides. The left side, the derivative, that's going to be 3x squared minus 1. Yeah? And on the right side, to find the average rate of change, well, I got to do a little bit of math over here. Plugging in, I get 8 minus 2 is 6. Minus plug in is 0. You get 0 all over 2 minus 0, which is 2. You've already shown your difference quotient, so feel free to call 2 minus 0, 2. Or call 6 minus 0, 6. Okay? Now, I would prefer that you kind of get both sides simplified as much as possible first. And the reason is you are now staring at 3 on the right side. That is the average rate of change of the function. Okay, so you know what that is. On average, it goes up 3 over 1, up 3 over 1. But does it actually get there that way? Probably not, because it's curvy. You didn't drive 55 miles per hour the entire time, right? Because that would be one heck of the way to leave the driveway, right? Now we can solve it. Now we can use algebraic methods to solve it. So there's only one x in there, so this is where we would separate. Oops, do it correctly though. This is where we would isolate and separate the variables, and you get x squared equals 4/3. And now if we take the square root, do we want to at least consider always plus or minus? Yes, you always have to consider. And you get the square root of 4/3, which is going to be the same as plus or minus 2 over the square root of 3, which is the same as plus or minus 2 square root of 3/3. Either one of these down here would be kind of acceptable. You don't necessarily need to rationalize anymore. Now, do we box both of them up and walk away? No, and this is where you need to be careful again. It says to find the values guaranteed by the theorem. The theorem tells us that our x values that we're looking for have to be strictly between 0 and 2. Are both of our values strictly between 0 and 2? No. So since I did it as plus or minus, I can't really x one out. So I'll say, so the value is x equal, and there's only one of them, right? Which one do we want, the positive or the negative? The positive. 2 square root of 3/3. Uh-oh, I don't have a calculator, though. How am I supposed to know that that number is actually between 0 and 2? Oh, you could try to calculate it all you want. That might be a pretty good argument. But how do I know that it's right? It has to. It has to be there. Yeah, it has. No, yeah, 2 times the square root of 3/3 is between 0 and 2. You can do it that way, too, because you have a mental calculator in your brain. I don't. But I know that it has to be there. Because the other one was definitely outside the interval. It was a negative, so I got that one. And there's only one left. And the theorem, of course, what? Guarantees one. And if that's the only one that's left, congratulations. You're it. Right? Yeah. You want to see what it looks like? Do we have time? I don't think so. We're in here till when? 20? We're in here till 20? Okay, good. Well, if I said it, then it must be truth. I guess. Not really, but hey, let's do something. Let's write the equation of the secant line. Can we do that? Do we know how to write the equation of a line? Do we know? Yeah, do we know? We do. Yeah. So let's use, which point do you want to use? You want to use the point at 0 or the point at 2? 0? Okay, so that would be the point 0, comma 0. Oh, that's sweet. Okay. And then what's the slope of the secant line? 3. I highlighted it over there. Remember that? So the equation in Taylor form of the secant line is y equals the y value plus the slope 3 times x minus the x value. That's just y equals 3x. Now, here's what I'm going to do, the last thing, before we have to go. I like looking at pictures. That's why I get the Herald. No. I get it for y'all's pictures. When y'all's picture's in the paper, I cut it out and I put it on my refrigerator. Oh, on that not my refrigerator at home. That'd be weird if you came to my house and I had y'all's picture on my refrigerator. Yeah. No, the one over there in the classroom refrigerator. Okay, yeah, no, I'm glad you did because I wouldn't want anyone to think the other one. Yeah. Hey, would you like to come over to my house and get a soda? What the? All right. Anyway, I graphed the function and I graphed the line, and I'm going to graph them in the window from 0 to 2. Now, I'm going to hit zoom. Well, I don't want to do zoom 6 because that'll mess my window up. I'm going to, let's see, what do we know about the y values? F of 0 was 6. Let's go from, let's try negative 10 to 10. That function may dip down, may go up. Oh, that's the scale. I'll turn that one to 0 or 10. 10 is fine. 10 is fine. Yeah, negative 10, and this one should be 10. Okay, and we'll leave the scale at 10. Why not? So I'll graph it, and all right, so I can adjust my scale. But you'll see what happens here. It looks just like a bow, doesn't it? Because I've graphed it, I don't even need to rescale it. That looks good. Because I've graphed it strictly from the window that I'm interested in, this red line connects the graph perfectly at the endpoints of my graph, which I would expect it to do because it's the slope of the secant line. So what we're saying then is that somewhere on this interval, and we know where it's at 2 square root of 3/3, the slope of the red line is parallel to the slope of the tangent line. Let's hit trace and type in on the blue graph 2 square root of 3 divided by 3. That's the value. Is that right? Does that look right? If I were to slide that red, we could find the equation of the tangent line, right? I just didn't want to have, there's the point. I didn't want to have to plug that ugly y value in to get the equation. But if I slide this tangent line down, right there, you'll see that? You don't see it at home, but you could do it at home. At home, grab a little ruler. Don't grab one that's 3 feet because that'll probably not fit on your computer screen. Grab like a micro ruler, like a little 1 foot long ruler, and slide a ruler. Have a ruler and slide it down parallel. Be careful. There you go. Get your parents out to hold the other end for you so you can keep it steady as you slide it down parallel. And right there where it's blinking, you'll see the tangent line. And I'll leave it to you as a special activity to find the equation of the tangent line. No. Do we have time to do that? I think we can. Let's do it. No. Well, I'm doing it. The equation of the tangent line, it's going to be y equals the y value. This is what I was trying to avoid. The y value would be 2 cube root of 3 cubed minus 2 cube root of 3/3. Oh, I did. So let's just not do it. The bell's sneaking up on me, and I hate that. I just, my amygdala goes crazy. Micro ruler. Okay, we're done. Obviously, we're done. We'll pick up with example 3 on Monday. Yeah, and I'll kind of expect y'all to have that equation of the tangent line for me then, as for that special activity.